actually. Yeah, go ahead and hand them out. They're sort of collated so that you can grab off a stack of 3 sheets. Yeah, so we're going to introduce Fourier series. So we're in chapter 15. I know there's an exam on Friday that only goes to chapter 14, and I realize that it's going to be really hard for you guys to focus in on chapter 15. But in order to help you with that, we are going to have a homework assignment due Wednesday of the week we return, so on this stuff. So you are going to, there's a reason that we're doing this. You're going to get to do homework on it. And there's a reason you're going to do your homework. You're going to get to do an exam on it. There's a reason you get to do your exam on it. Oh, wait, I ran out of reasons. I'm kidding.
Wait, so is there a homework assignment this week?
No. Yeah, there is one this week. There is.
Very long now, so
So
there's the usual is due on Wednesday this week. Then we have a homework assignment to do on the new stuff that's not on the test the week after we get back.
that's true.
All right.
Yes. So assignments. So I did update. I added one problem to the assignment for this week. It's so that you guys get practice doing the Bode plots, sketching the Bode plots, because I think it'll help you on the exam. So I added a couple other problems that are suggested, and they won't be on the quiz, but I think that they will help you study. So I put them on there so that if you do the problems, it'll help you study for the exam. So, all right, so they're just suggested down here, but I did add one in there that will be on the quiz. Just sketching Bode plots. And I did that so that you guys would be prepared for the exam. No other reason. I don't hate you or anything like that, I promise. Alright, so where are we? Oh yes. We are here. So I'm going to be talking about chapter 15 stuff today, Fourier series analysis, and I'm going to actually introduce it by showing you some notes from the resources section of the website. So does everybody know how to get to the resources section of the website?
I don't.
On the main page, I will show you then. The main page, go to Resources, and then click on the link. And then go to the System Dynamics Notes. So click on that. It'll open up this PDF. I have already brought us to this point. Oh, thank you. So it brought us to this point, which is, I don't know what page of the notes, page 18 of the notes. And section 14, which is on Fourier Analysis of Periodic Waveforms, or the Fourier series. So this section, I'm just going to introduce it by kind of going through this column here, and then we're going to do an example. So we're just going to jump right in and start using it. It feels very mathy at first, but it's very practical, and there are lots of applications for this. So a periodic function is one that satisfies this equality. So for all values of n at integers, positive and negative integers, n, the function at some given time is equal to the function at some given time plus n times t, where t is the period of the function, right? So it's equal to itself if you go one period away, or any number of periods away. The fundamental frequency, omega 0, is defined as 2 pi divided by the period, okay? So that is the period that we've always known and loved about for periodic functions. Like, so what is an example of a periodic function? Sine. Excellent. So the fundamental frequency is just 2 pi divided by the period, which you guys have always just called the frequency of a periodic function, but we're going to learn about more frequencies associated with it. So we call it the fundamental frequency. Waveforms are called harmonics of each other if their fundamental frequencies or periods are an integer ratio, meaning the greater divided by the smaller equals an integer. Okay? So these always show up as multiples of the fundamental frequency. So there are a bunch of harmonics in some waveform. So say you have a periodic waveform and it like repeats some weird squiggle over and over again. There's the fundamental frequency, 2 pi over t. And then there are harmonics, higher harmonics, where you multiply that fundamental frequency by an integer and you get higher harmonics, okay? So we'll be using that terminology. The Fourier series is a description of a periodic function as a weighted sum of harmonic sinusoidal components. Okay? The nth harmonic component of the series can be written as, so say you have this series and they're all summed up. This is the nth term in the series, okay? It's some coefficient times cosine n omega naught t. So notice that this n omega naught is going to be some multiple of the fundamental frequency, right? So it's going to be a harmonic. That means it's going to be a harmonic. And we're going to sum up these terms with cosine and a sine at that frequency and different coefficients. And like we've talked about before, you can rewrite a sine and a cosine that are added together as a single sinusoid. So I'll use script A sub n to be the amplitude of that sinusoid, and then we have a phase shift. So you can write it like that, which is our preferred form, where the conversions between the representations are as follows. So I just give you how to go from this representation in 173 to this representation in 174 and vice versa. So that's with those two. 175 and 176 just show you how to convert from one form to the other. Okay? Now, the Fourier series representation of a function f of t, subject to certain conditions, see page 509 in the text if you want to see what those conditions are, is this, okay? So we can either, so let's ignore this first term. We can either write it as a sum of these cosine plus sine terms, or we can write it as a sum of sine terms with this phase shift and different amplitude in it. And then we also have this term out front, which is, so 1/2 a naught. That we're going to find is sort of like the DC offset of the signal, okay? Now, big rip in the shirt. Just saw it out of the corner of my eye. So what we're doing, I mean, it's kind of crazy, right? What we're saying is that we can represent a function that's periodic. So if it's a periodic function, even if it's some weird squiggle or whatever, we can represent it as a sum of sinusoidal terms. Now, notice this isn't an infinite sum, so there are a lot of terms, but we can do it nonetheless, which is pretty radical, right? Saying like, okay, we have this one type of function, sinusoid. We can write other functions as just like a sum of a bunch of these sinusoids. That is not obvious that you could do that. I mean, it's not obvious to me. I don't think it's obvious to most people that you could do that. So it's a pretty radical thing, but it works. And we're going to see an example of that today, of it just working. And I don't want to get bogged down in the mechanics of this because the math, you have to compute things for this, like an integral and all of this stuff. You have to compute things for it. But the big level picture here is that you can represent a signal, a periodic signal, as a sum of sinusoids. Okay, that's the big high-level view. And we're going to use that on Wednesday. We're going to use that idea to extend our understanding of the frequency response of a system, okay, by saying, oh, well, if we mash this idea of any signal being represented by a sum of sinusoids together with the idea that we have superposition, where you could break down a function into a bunch of components, find the response of a linear system to each of those components separately, and then sum them up. Well, what we're going to find is we can essentially look at the response of any periodic function as being a sum of sinusoids, and therefore we can use our frequency response function, which we've been talking about quite a bit, not just for sinusoidal inputs, but for any periodic input. Okay? And then we're going to go one step further. We're looking ahead here to after spring break. We're going to go one step further, and we're going to find what's called the Fourier transform, which can represent not just periodic signals, but aperiodic signals. And that will also be a sort of sum of sinusoids, but it's continuous and not discrete. And that is going to get us all the way to thinking completely in terms of the frequency response function and seeing our systems as being these frequency filters, all of them. Okay, so although it seems like at first the frequency response function is only useful for sinusoidal inputs, it's actually useful for all inputs, as we'll learn. So that's just looking forward, but for now we're back just trying to learn the mechanics of writing this Fourier series. Okay, so saying that it exists is cool, but then we got to compute it, right? So we got to learn how to do that, but it's just maths. So no problem. So there's another representation. So if we have sinusoidal stuff, there's always this complex exponential that's Euler's formula allows us to convert to. That's always lurking in the background, right? And sure enough, we can also represent this sum of sinusoids as a complex exponential sum. So instead of summing over the cosines and sines, you sum over these complex exponentials. And that has coefficients of its own, where fn and f minus n are related to an and bn in these ways. So an and bn are our original cosine and sine terms, right? And fn's are related to the an's and bn's through this formula, which is a result of Euler's formula, okay, distilled down. So it allows you to convert. Once again, so 175 and 176 allow you to convert from the lowercase an and lowercase bn to uppercase an and phi n, right? And 182 and 183 allow you to convert, 180 and 181 allow you to convert from an's and bn's to fn's. Okay? Okay, lots of conversions, lots of formulas, but once again, it's just maths, and we know how to do the maths. We just need to use the right maths in each particular place, but no big deal. So, we have a representation of any periodic function as a weighted sum of sinusoids. To determine the weights, the coefficients, the following formulas can be used. For the real representations, you can compute the lowercase an and bn terms as these integrals, okay? So you have to plug in the function, the periodic function, into this integral. Surely the weights are related to the original function that you're finding the periodic sum representation of, right? The Fourier series representation of. So we integrate that over one period. So I'm integrating from t1 to t1 plus a period. So you can choose any period to integrate over. It's totally valid. And if you integrate over a period, then you integrate the function over a period multiplied by cosine of n omega naught t. This is not obvious either, but this comes from a, not too lengthy, but somewhat involved derivation that I'm not going to make you guys be subjected to. But this is the result, that you can compute these coefficients using these formulas. And A0 can be computed separately from equation 182. So if you plug in n equals 0 here, then cosine of 0 is 1, and you have to integrate over f of t by itself to find A0. Fn has this complex representation here, where you integrate over f of t, but you multiply it not by cosine or sine, but by this actually imaginary exponential, right? F minus n is the complex conjugate of fn, so we don't have to compute them both. We could just compute fn and then take the complex conjugates to be the minus ones. That's a sort of shortcut. And f0 can be computed separately with n equals 0. When n equals 0, this is e to the 0, which is 1. So you're integrating over f of t again. Whew! All right. Integrals. Man, you guys are like really hoping that this lecture today would have integrals in it. I know. You're welcome. Okay. So we've learned the definitions, and we've learned how to compute ANs and BNs and FNs. And in a moment, we're going to do a problem where we actually do this. We compute them. Okay? We're almost ready for that already. No problem. We just breezed right through the theory. But I do want, before we go on to that, I do want to talk about a couple properties of the Fourier series. Okay? So, here are a few of them. These are the ones that I found to be most pertinent for our discussions. The first one is linearity. So if the Fourier series components of two periodic functions, g and h, with identical periods t are r, gn, and hn, then if a new function f of t is defined as a linear combination of g and h, such as in 185, the Fourier components are just the linear combination of Fourier components. So that's nice. That's convenient. It allows you to build Fourier series representations from simpler ones, so you can build a more complex one by just summing and scaling them. Okay. We're not going to spend a ton of time getting into really complicated ways of doing Fourier series stuff, but it is useful to understand how to do basic ones at least. It gives you the real takeaway is, so it's useful as a tool to represent a function this way, but I actually think that its real power is the intuition it gives you for how to think about a function as being a bunch of sinusoids summed up. And that is a really nice way to get you thinking in terms of the frequency domain, okay? Where the dynamic system is this frequency response function that's filtering input frequencies through its frequency response function to give you output frequencies. So it's useful as a tool, but it's most useful as a way of gaining intuition for how systems respond. Okay, and that's why I teach you this. You can learn how to compute things, and actually, I mean, to go off on a little tangent, you may recall back in mechatronics when we taught, we did that one lab where we had different sinusoidal inputs going into a circuit, and then we would look at the steady state response of the output. And we saw that at different frequencies of the input, different frequencies of the output came out. And you could compute those way back then, okay? And you could compute them because you could solve for the steady state solution. You could solve for the total solution, and you could find the steady state aspect of it and compute what those amplitudes are. So you could do that way back in mechatronics. It's not that we can't do these things with the other way of thinking, with the time domain way of thinking. It's just that we don't get the intuition about how systems respond via frequency in that mode when we think of in those terms. So now we're learning how to think of them in a different way. It's kind of a paradigm shift, and I want to make sure that we don't get lost in the weeds of computing these things. I want to make sure that we see the big picture. So the next property that's nice is if the function is even. You guys are really going to like this one. If the function is even, then all the bn's are 0. So all the bn's are all the sine coefficients, right? So if it's an even function, all the sine terms go to 0. Do you remember? So sine and cosine, one of them is even, one of them is odd. Do you remember which one's which? Sine is odd and cosine is even. So it makes sense that the odd function, when you have a function you're trying to represent that's even, you don't need any of the sinusoid terms. They all go away. All the odd ones go away. You only use even ones. And the reverse is true as well. If the function that you're trying to represent is odd, then all of the cosine terms, which is an even function, they all go away. We don't need any of those to represent it. Note that if a function would be odd if it was shifted up or down by some DC value, so some offset vertically, assume that an equals 0, do the analysis with all of your either an's or bn's equal to 0, and then do a shift at the end by an a0, okay? By the 0 term that offsets things. So there's a little bit more interpretation of the 0 term here. So interpretation of the 0 frequency, or sometimes called the DC term A0 or F0. So this term is simply the average value of the function over a period, right? We found that to be true when we looked at what happens when n is 0. The cosine term went to 1, and we just integrated over the function for a period. Same is true for when you are in the complex representation. It's e to the 0, which is 1, and you end up integrating just over the function for a period. So it's simply the average value over a period, which is what happens. So I don't know if you guys know this, but if you want to average a signal over a period, you just integrate it over that period. That's the average signal. If a function is shifted up or down, this is the only term in the series that is affected, and it is shifted by the same average or DC value. Okay, so that's that like vertical shifting thing again. We can just shift things up and down by adding a term, like we always have. And we can take advantage of the even and odd aspect and not compute as many things. So since we're computing integrals, you guys would probably want to get out of computing as many as you can. So using these properties helps you get out of computing quite so many integrals, which is nice. Okay, so that is all of the theory we're going to use for the Fourier series section of our discussion. So we might have to come back to that, but for now, let's switch over to the Fourier series example. So, okay, consider the square wave function shown at right, okay? So this thing is negative c. I'm just leaving it as c. I could make it negative 1 or whatever, but I'm just saying c because it's some constant. Negative c for negative t over 2, where t I haven't specified, but some period. I'm just not going to give you a period because I like to keep things general when I can. So from negative t over 2 to 2, it goes negative c to positive c halfway through the period, right? So this is a square wave. We've seen square waves. In mechatronics, we did some square waves, right? If you want to write it mathematically, we would say that it's positive c for time is 0 to t over 2, and negative c for t over 2 to t, where I'm using the mod function, which essentially divides whatever the time value is by down into the period that it's in. So it's like the remainder function. Okay, so we apply the equations of the Fourier analysis. So we're going to use, we could use any of the three representations that we have, right? We have to compute the either the ANs and BNs or the FNs, okay? We have to compute some of them. So we're going to go with the cosine and sine ones this time, so the ANs and BNs. Now, when we look at our problem, can we get away with getting rid of something because it's even or odd? Do you guys remember what even and odd is to find out? Do you guys remember the definition? Okay. Let's remind ourselves. So an even function is a function like x squared, for instance. Whoa, it's symmetric about the vertical axis, and it has the property that f of positive t, let's say, is equal to f of negative t. What?
That's even, right?
That is even. Yes, this is even. That's even. So cosine is even because it's like this, right? It goes up and then down and then up and then down, up, like that. So it's, if you go to like positive pi, it's the same as negative pi. Okay? An odd function mathematically, f of t is equal to negative f of negative t. Okay? So that is
Like a cubic function?
like a cubic function, yeah. So if you go to positive 1, you evaluate it, say it comes out to like, well, it comes out to 1 if it's x cubed, right? If you go to negative 1, it should be negative 1 is the value that should come out. If you go to positive 2, you're going to get 8 out, right? X cubed. You go to negative 2, you're going to get negative 8 out. So that's an odd function. And sine is odd because we have this sort of action here, like that. And if you go to any positive value, go to positive pi, it's equal to negative pi, etc. Negative pi. Ugh. Yeah, the negative of the other one. Anyways, it works. It's really it's something kind of basic from back in the day, but it really helps if we don't have to go through the integral, because we could say, oh, this is an odd function, right? So you always come back to the definition. The thing about, the way that I remember if a function is odd is if you broke it at the origin and you took the right half of it and you rotated it about the origin, it should lay on top of itself. So say that you broke it right here, and you just hinged all this right-hand stuff, and you rotated it around, it should match up with itself on the other side. The even one's easier because it's symmetric about the y-axis. This one is, I forget what they call it, rotationally symmetric, something like that. Rotational symmetry. Some people don't find that idea of hinging something and moving it easy to do in your mind, but if it is, go with that. If not, you can use the definition. You could evaluate a few points, get a feel for it. Okay. So this is an odd function. So we are going to apply the equations of Fourier analysis. So we could go through and compute what a n is, right? Let's compute what a0 is just for fun, and then we're not going to compute the other a's because we're going to say, oh, well, they're all going to have this same thing happen. So a0 is defined as being, from the equation, 2 over t integral from, you can integrate over any period, okay? So the period I'm going to choose is from negative t over 2 to t over 2. You could choose 0 to t if you want. Doesn't matter. So I'm choosing negative t over 2 to t over 2. Obviously, choose a period that makes sense for integration. So in this case, you can't integrate this. It's not a continuous function, right? So you can't integrate it through this discontinuity without breaking it into an integral over the different regions, right? So I would encourage you, in this case, not to choose t over 4 to 3t over, or whatever, from t over 4 to 1 and a quarter t. That just wouldn't make sense, because then you have to break it into 3 intervals, whereas you can break it into 2 intervals if you start from negative t over 2 and go to t over 2, or if you go from 0 to t. If you didn't follow that argument, don't worry about it. It's not a big deal. So it's just it's a way of making your integral easier. It's not fundamentally important. So technically we should use a dummy variable when we integrate over y. And then if you have, this term has a cosine, technically, cosine n omega t. Cosine of 0 is 1, so we're just going to get rid of it. Okay, what happens if you integrate this function from negative t over 2 to t over 2? What is it equal to? 0, right? Sweet. Love it when that happens.
Do that again.
Ah, okay. So the area from negative t over 2 to 0 is going to be this area, right? And it's completely canceled by the area from 0 to t over 2, because it's going to be the same area, but it's going to be negative in the first part, so this region, and then it's going to be positive in this region, so they cancel.
So, would we do 2 intervals?
You would, so you would do it if you wanted to make sure. You could break it down as the integral from negative t over 2 to 0, and do that integral. The integral of a constant, just finding the area under this curve, which is just rectangular, so you could do base times height, right? So you could do base times height, which is going to give you negative c times t over 2. Okay, that's the area here. And then this area is going to be positive c times t over 2. The integral will come out to be that, just the area. And so you're going to sum them together,
Still equals 0.
and it equals 0. Because they add the negative area cancels with the positive area. Just like if you integrated sine from negative pi to positive pi, the negative area would cancel the positive area, and then you would get 0. Yeah, so just like that. And in fact, it turns out that all of the ANs, because of this, we could go through and compute it. And actually, I did in my notes, I computed it, but it's always going to end up being 0 based on that property that if we have an odd function, which we do, then all of the ANs are going to be 0. Sweet. Okay. That just leaves us with the BNs, which better not all be 0, otherwise we're going to have an issue. So we screwed up somewhere. So Bn, by definition, is equal to 2 over big T times the integral from minus t over 2 to t over 2. So I choose that same period again to integrate over. Y of t, and then this time we have to multiply by cosine of 2 pi n t over big T. In the formula it says, so let's switch over to the formula. In the formula it says n omega naught t, right? I am saying that instead of plugging in n omega naught, I'm saying omega naught from the definition of omega naught, which was up here. This is 2 pi over t, right? So I just plugged it in. 2 pi over t. And then dt. I should use a dummy variable, but I didn't, so I'm not going to go back and do it. So we have that definition. So we need to compute this integral. And ideally, we can compute it without having to choose what n is, right? Then we could compute all of the terms, all of the Bn terms at one time. I know. This is really, it's entertaining. So let's do this. Do we have a game plan, a strategy for how to compute this integral? So once again, we don't want to integrate through these discontinuities. We want to integrate from, say, let's choose from negative t over 2 to 0, and then from 0 to t over 2 as our two intervals, and we'll integrate over them separately. Remember, an integral, you can always break it up like that. You can sum the integral from one spot to another spot with the integral from that spot to the next spot. So you can always do that. So let's do it. So we're going to have 2 over t, which is going to multiply everything. So then we'll put a big parenthesis. And we'll integrate from negative t over 2 to 0. And what is y of t in that region from negative t over 2 to 0? It's just negative c. So we'll just plug in negative c times cosine of 2 pi n t divided by t dt. And then we're going to add the integral from 0 to t over 2. And what is y of t during that? C. Cosine 2 pi n t over t dt. Close that parenthesis. So these look like integrals we could do, right? Because this is a constant, this is a constant. So let's pull out the c. So 2c, it shows up in both terms, right? The c, the constant. And since it's a constant, it can come outside the integral and be factored out. Now, this is, I'll rewrite it just to not take too many steps at once. I like to take lots of steps at once, but we're just going to use...
I don't.
Okay. Jordan doesn't like it, so we won't Oh yes, there was somebody who noticed a mistake. This should be a negative sign there, right? So I'll pull it out of the integral and put it right here. Okay, so we've got that. Notice that these are both, they're the same integral, they just have different limits, right? So oh my goodness, you guys. Did we screw up? Did we screw up? Where did we screw up? We've been using cosine all of these times. I told you that we were doing bn's and not an's. The cosines are always going to come out to be 0, right? We talked about that. I meant to say that the cosines are all going to be 0. The an terms always have the cosines in them. So if we go back to here, the an terms always have, an terms have the cosines in them. The bn's have the sines. Since the an's are the cosines are even functions. We have an odd function. All the even ones are going to be 0. So wherever we wrote a cosine, so everything that we've done is actually still valid, right? But we just need to just delete all of our cosines and write sine instead. So all of these places we wrote cosine, let's just delete them.
So it's find and replace, right?
Yeah, just find and replace. And we'll put in a sine. Because we could have finished that calculation, but that was all for an, right? We're looking for bn. Sine. Sine. Right.
You'd have, if you're looking from like 0 to pi, wouldn't those both be above the x-axis?
Yes, they would. But then you're going to have a positive and a negative. And then they're going to just be equal and opposite, and they're going to cancel out. The sign actually doesn't. So you could compute it. I mean, we had it written down. You could compute it. It comes out to be 0. Let's compute it for the sine one. Okay. So I'm going to leave as an exercise finding the integral of each. I mean, if you integrate sine, you get cosine. If you integrate cosine, you get sine, right? And you have to do the evaluation of the limits. You have to add them. And it's a little bit messy. It's not a ton of work, but it's a little bit messy. I'm going to tell you that you can simplify that down to the following, because I don't want to get bogged down in those details. You can simplify it down to this expression. So, yeah, of n pi. So it's 2c over t times 1 minus cosine n pi. Now, that expression is something that we can simplify even further. I mean, these are the bn's, but we can compute this for even and odd values of n and get something that makes sense. So what happens if n is even? That means that n is equal to, say, 0, 2, 4, 8, 6, 42. All multiples of 2 pi, right? What is cosine of those? 1. 1 minus 1 is? 0. For n even. So hopefully for n odd, that doesn't happen. What happens if n is odd? So say n is 1. What is cosine of pi? 0. So we're going to have 1 minus 0, which is 1. So we get 2c over t. And then if you did cosine of any of these multiples here, so, oh wait, I forgot. This was not just t, this was n pi. When you compute it out, the t actually goes away, and you get n pi. So same still holds. 0 times anything is going to be 0. So, but in the second part, we have 2c. So if cosine, well, cosine of pi, wait, we said cosine of pi is 0? It's negative 1. Which is, so that's 1 plus 1 is 2 times 2 is 4, c divided by n pi. And that's true of every time that we have an odd value of n. So it ends up being 4c over n pi.
It's not over pi squared. Because you made n pi. Or is it just the general cases?
This is for all cases. So I didn't make t n pi. It just falls out. T falls out. So my little aside here was what we said. an equals a0 equals 0 for y of t odd, and bn equals 0 for y of t even. Okay. So we've computed the coefficients. We've computed all of these coefficients, the ANs and the BNs. ANs are all 0, A0 is 0. BNs are 4c over n pi for n odd and 0 for n even. Okay?
Do you care about the bn equals 4c over n pi for odd?
Do we care about that?
Yeah.
Yeah. So those are the only harmonics that show up are the odd ends. So we're, it's a very that's sort of a piece of information that we wanted to know is where are the harmonics that show up. We kind of suspected we couldn't just just use a sine wave to represent this. Maybe we're going to need more than that. So Fourier synthesis goes as follows. So we did the analysis, which is the part where we wrote it as components, ANs and BNs, etc. So we can synthesize the first p terms of the series. The full series is A0 divided by 2. So this is all straight out of the formula here. So I'm just writing equation 177 here. A0 divided by 2 plus the sum from n equals 1 to infinity of an cosine n omega, or n pi, well, there's the 2 in there. So I should do 2 pi n t over t plus bn sine 2 pi n t over t. We computed an and bn, so we can compute these. All the a's were 0, so we can just say this is equal to n equals 1 to infinity of bn sine 2 pi n t over t. So we can say that for sufficiently large values of p, we can sum up just the first p terms. And we should get an approximation of y. Okay? So that's our idea of the sinusoid representing it. Even if you get just the first number of them, we'll see. So let's compute the first few harmonic amplitudes. So we'll write first harmonic, and then we'll do second harmonic, third harmonic, etc. So what is B1? So we computed B, right? Is B1 odd or even? So odd. And then n is 1. So it's 4c over pi. And then B2 is what? 0. B3 is 4c over what? 3 pi. Because B is 3 in this case. B4 is 0. B5 is 4c over 5 pi. Very good. So notice something. We are decreasing in amplitude here, right? So the higher harmonics have less effect. So the very first harmonic was 4c. As we increase n, we're dividing by n, right? So it gets smaller and smaller. We can visualize these harmonic contributions on a frequency spectrum as follows. So if we have so first off, let's compute this script a(n), which is the square root of the an squared plus bn squared. This is writing it as a single sinusoid. Notice that in this case, all the an's are 0, so we just have the square root of bn squared, which is just the absolute value of bn. So we're just going to write the absolute value of bn on all of these. So what is our b1? It comes out to be, so I'll just write b1 here, 4c over pi. And then b2 is 0. Oh, what was our a0? What was our a0 that came out? It was 0, right? We computed it. It was 0. So at 3, at the third harmonic, we had B3, right? So B3, and then we had 0, and then we have B5, and then we have 0, and then we have B7, and 0, and B8. So these things fell off really quickly, like a 1 over x sort of falling off. So thinking about the signal y of t in terms of its harmonics and its frequency spectrum is common practice. So we think about it as being, so this signal, oh, okay, it's a square wave. But also in the frequency domain, so time domain it's a square wave. In the frequency domain, it looks like, this descending harmonics, okay? And now I just want to talk about visualizing this. We're trying to visualize the summation of the harmonics in the Fourier series. So if we use the first harmonic, this is what it comes out to be. It just looks like a sine wave that's just stuck on top of it, of the square wave. But if we keep increasing it, so say if you go up to p equals 3, so that's, you have 3 terms. Notice that it got a wiggle in it, but it started to sort of get a little bit closer to square wave. As you increase it, it gets a little bit more closer, a little bit closer, and a little bit closer. Once you get to 9 terms, it's looking a little bit like a square wave. I did it up to 13, and you get this. Notice that the amplitude gets a little bit peaky right at these transitions. This is called, at discontinuity, this is called Gibbs phenomenon. But the important thing is that you can represent it as a sum of sines and cosines. And there's a Mathematica script that I wrote up that does all of this. And so you can see with a bunch of terms, how many terms did I do there? 200 terms. You can go up to something that looks like that. And that's the one that I use to generate these graphs. So you can play around with it. And that's Fourier series. It's really cool. We're going to use it on Wednesday, okay? Thanks for sticking around for the extra bonus part of the lecture. I appreciate it.